In this second part of the program, we're going to cover in detail the operation and use of overloads. Then we'll continue with the controlling of motor operations, 2- and 3-wire control, and the causes that make motors fail. So let's start by taking a look at overloads. As we have mentioned before, motors are required to have protection against overload situations when the motor draws excessive current for a period of time. By drawing excessive current, we don't mean when it first starts off, where the inrush current is expected. This excessive current occurs when the motor is overloaded due perhaps to a motor stopping rotation because of a jamming condition in the line. When overloading occurs in a motor, it will produce overheating, resulting in a deterioration of its insulation and cause damage to the motor. A motor can also overheat if it is started and stopped too frequently. To meet the protection requirements of a motor, overload relays provide 1. A time delay to allow the harmless temporary overcurrent during startup. 2. Tripping capability of the motor circuit once a dangerous level of overcurrent has been detected for a period of time. And 3. They provide a means for resetting the circuit. Overload relays are represented by this symbol, although you'll also see them usually represented with this S symbol. We already know that the overload contacts from overload relays are represented like this. Overloads are illustrated like this in a single-pole, one-phase, two-pole, one-phase, and a three-pole, three-phase motor circuit. There are two main types of overload relays: the mechanical, operated by a heater element, and the solid state. The assembly of the overload relay is formed by the heater coil, also called overload heater, and the contact mechanism. Although there are different types of heaters by different manufacturers, all of them work under the same principle of measuring the heat generated by the current passing through. There are two design types which are commonly used. These are the eutectic melting alloy and the bimetal overload relays. The eutectic melting alloy overload uses a heater element which surrounds a solder-like mechanism that holds the pin of a ratchet wheel element. The term eutectic simply means low melting temperature solder. When excessive current passes through the heater, the solder will melt and will transform into a liquid state very quickly without going through a plastic range. This will cause the ratchet wheel to release a pawl it is holding. Once the pawl is released with pressure of the loaded spring, the normally closed contacts will open. When the solder-like melting alloy has cooled down to a solid state, the overload relay contacts can be reset to the normal state. If you try to reset it while the alloy is still liquid, the contacts will open because the ratchet will not be able to hold the pawl mechanism. The bimetal overload relay operates in a very similar manner, except that it uses a bimetal strip made of two bonded metals which expand with heat. This heat is the result of overload current created by the heater element and transferred to the bimetal element. When the overload condition is detected, the bimetal element will bend and open the normally closed overload contacts. After the bimetal has cooled off from the heat created by the current, it may return to its original position automatically or manually, depending on the assembly. It is important to mention that the automatic resetting feature of these overloads is restricted according to Article 430-43 of the National Electric Code, because of potential damage to personnel and equipment due to an automatic restart of a motor. These overload relays will disconnect the motor from the circuit as soon as the heater coils detect enough current to disengage the normally closed contacts. Therefore, it is of extreme importance that the heater elements be properly sized. We'll see more on this in a short while. The solid-state overload relay is represented like this in a motor circuit. This overload relay provides the same action as the heaters. It detects overcurrents by sensing the AC current magnetically from the motor leads which pass through its current loops. This overload assembly provides automatic reset, therefore making necessary additional circuitry to provide for the manual reset. The greatest advantage that it provides is that this assembly is unaffected by ambient temperature, as heater coils are, thus eliminating nuisance tripping during hot days. This Furnace ESP100 is an example of a motor starter which provides protection using a solid-state overload relay. This relay, however, does provide manual reset and includes adjustable trip current setting from 13 to 27 amps. The National Electric Code specifies the amount of protection that must be provided to a motor. For example, a three-phase AC induction motor with a service factor of 1.15 would require, according to code, 3 overloads selecting to trip at no more than 125% of the motor's full load current rating. The selection of the heater component part is your responsibility, and its sizing is indeed of tremendous importance. The standard tripping curves of heater elements are specified at an ambient temperature of 40 degrees Celsius to correspond with the temperature at which most motors are specified for ambient conditions. Underwriter's Laboratory requires, at a temperature of 40 degrees, that an overload relay trip in 4 hours of operation at 100% the trip current, in 8 minutes at 200%, and in 30 seconds at 600%. Heater elements are rated by NEMA according to the amount of time it would take to melt the alloy when the motor is drawing 6 times the full load current. These heaters are grouped in 3 categories, which are Class 10, Class 20, and Class 30. The Class 10 will melt the alloy in 10 seconds, the Class 20 in 20 seconds, while the Class 30 will melt it in 30 seconds. Class 10 heaters should be used in applications to protect hermetic motors like compressors and air conditioning systems, submersible pumps, and other motors with short locked rotor times. The Class 20 heaters are the most popular, being used in general applications, while the Class 30 should be used in motor applications with high inertial loads such as driving grinding wheels, flywheels, and others. Manufacturers provide tables which give you a reference for the use of the proper heater for a motor pulling the indicated amount of current. Just make sure that the heater you are referencing to the table has the proper current for it, whether it is already calculated at 125% of the full load current or if it is calculated without the 125% required by the code. Thermal overloads are sensitive, as we have mentioned, to heat, and they do get affected by the ambient temperature. For example, if the total heat required by the overload relay to trip is represented here, and the ambient temperature creates this heat, then the rest of the heat is left for overcurrents due to an overload. The motor draws the full load current for a long period. The overload relay will trip. Now, if the ambient heat is this much, then the overload will trip at less overcurrent, creating a nuisance tripping. Conversely, if the ambient heat is this much, then the amount of heat necessary by the heater will be this much, however requiring more current than necessary to protect the motor. This can result in the burning of the motor due to overheating because of too much current. Bimetal overloads may provide a compensating bimetal strip which is added to the assembly. This compensating strip allows the relay to adjust for changes in ambient temperature at the location of the overload assembly, which is usually close to the motor starter. This curve indicates the relationship of ambient temperature versus the trip current. For example, at 40 degrees C or Celsius, a trip current of 10 amps will trip the heater, while at 60 degrees, the same heater will trip at 8 amps. At 20 degrees, the heater will trip at about 11.5 amps. A compensating overload relay will make the curve essentially flat across the different temperatures. Therefore, if you have an application where the motor is in a constant ambient and the overload is in a varying ambient, you should use a compensating overload relay. Most often, the control of circuits involve the control of motor operations from a simple on and off control to controlling the speed of the motor and the reversing of motor direction. In this section, we'll see how we can create a safer control circuit, understand wiring diagrams, and the use of 2- and 3-wire control circuits. Let's now look at how we go about creating a safer control circuit. Generally, control circuits show the power to be between L1 and L2, and usually show the voltage between the two lines, like 120 volts AC. This voltage we actually call the control power or control voltage. In many instances, we have applications using voltage supplies to motor circuits with 240 and 480 volts AC. In cases like this,
You may want to use lower voltage levels like 120 volts or lower for the control circuit for safety reasons. If a separate power source is being brought for the control circuit, then it must also have its own disconnect means. However, a lot of times what is done is to reduce the load supply voltage for use in the control circuit using a control transformer. These transformers have dual primary voltages of 240-480 volts with secondaries of 120 volts. Depending on how you connect the primary section, you will be able to transform 240 volts to 120 volts or from 480 volts to 120 volts, a 2-to-1 and 4-to-1 ratio respectively. Controlled transformers are relatively small and compact and are connected to the L1 and L2 supply lines of the motor power circuit in the primary side, while the secondary side is connected to the control circuit, usually through a fuse. Control transformers are designed to handle the high current inrush requirements of control relays, contactor and starter coils, solenoids, and other control devices. And it is highly recommended that when mounted, you leave sufficient airspace around the transformer to dissipate the heat. Also, beware that the primary wiring of 480 volts, for example, is not easily accessible to a person who may be troubleshooting the control circuit. These control transformers eliminate the need of bringing an additional power source to the control circuit. By adding the control transformer, we also eliminate the need of a separate disconnect means. Note that in this diagram, the transformer's primary connections are made after the disconnect means in the power circuit. Disconnecting the motor control circuit will also disconnect the motor load. Wiring diagrams, unlike ladder diagrams, are intended to show the actual connection and placement or location of components as close as possible, including the power circuits. Wiring diagrams are extremely useful to electricians and technicians while troubleshooting or designing a control system, since they provide you with a roadmap of the actual wiring. This is not more true than in motor control circuits, which, of course, use magnetic starters and other control devices. As we mentioned, the wiring diagram illustrates as close as possible the location of the wiring connections. In this starter, for example, you will find a wiring diagram like this, which shows all the connections to the starter, in addition to the location of the components within the starter. The symbols in the wiring diagram show the location of these components in the same manner where you would find them if you were looking at the starter from top to bottom. From the top, you have the three terminals that connect to L1, L2, and L3. Immediately below the power terminals, you will find another three terminals shown in smaller circles. These terminals represent and are used for the wiring connections of control circuits, which will be represented in thinner lines as opposed to heavy lines for the power circuits. We'll see these connections in a second. Right below, we find the actual contacts that will turn the motor load on, and below we have another set of terminals which are normally used when we have reversing circuit connections. These can be considered power connecting terminals, as opposed to control circuit terminals. Under this second set of power terminals, we find the starter coil represented in the diagram in the middle cross-section, which is the location where you will find it in the starter. Also shown are the two terminal connections that are used in the wiring of the control circuit. Note the smaller, thinner-lined circles which symbolize the terminal connections for the control circuit. When the coil is energized, the motor load contacts close, which in turn start the motor. On the left of the coil are located the auxiliary contacts, commonly used as interlocking or sealing contacts. The terminals are labeled 2 and 3. Depending on the starter, you may also have another set of auxiliary contacts normally open or normally closed. On the lower left, you'll also find the normally closed overload contacts. Depending on the starter, you may find 3 sets of overload contacts, one for each heater coil. If this is the case, you would connect or wire them in series if they do not come internally connected. Although most overload assemblies provide one set of normally closed contacts for all three power line circuits, if there is an overload in any of the three lines, the overload contacts will be tripped. At the right of the overload contacts in the diagram are represented the overload heaters, which control the overload contacts. Note that the terminal connectors for the heaters are in bold lines to signify the presence of a power circuit. Finally, below the heaters, you'll find the terminal connections T1, T2, and T3 that would be connected to the motor load. In this case, of course, the connections will be for a three-phase motor. Most of the time, you will find starters that come with some pre-wired control circuit connections, which are done at the time of manufacturing. These include one side of the starter coil to terminal 3 of the auxiliary contact. This connection will be represented in the wiring diagram like this. Another connection might be from the back side of the coil, so to speak, to the one side of the overloads. This connection will look like this in the wiring diagram. The other side of the overload will be connected to the L2 line in the control circuit, just as it is represented in the ladder diagram. As an exercise, let's come up with a wiring diagram for this 2 horsepower, 3-phase, 120-volt motor whose operation and control is represented by this ladder diagram. We can see in the ladder diagram that the stop push button is connected to L1. This is, of course, a control voltage. In the wiring diagram, we would bring one side of the stop push button to the L1 connection in the starter. Note that the connection is made to the small circle terminal to denote a control circuit connection. The other side of the stop is connected to one side of the start push button. This side is also connected to the number 2 terminal, which corresponds to the auxiliary set of contacts in the starter. These contacts are labeled M in the ladder diagram, and as can be seen, the numbers 2 and 3 of the starter connections are also included. This side of the start push button will be wired to the number 3 terminal of the auxiliary contacts. From the ladder diagram, we can see that this connection is also wired to the starter coil. The other side of the coil goes to one side of the overloads, and from the other side of the overloads, we connect to L2 to complete the circuit. These 2 wire connections, as we mentioned earlier, could already be wired in the starter when it was shipped from the manufacturer. Regardless, it must be shown in the wiring diagram. If we added a pilot light like this in the ladder diagram to indicate a motor on condition, we would include it in the wiring diagram coming from either this point in the push button or this point at the terminal number 3 connection. Let's connect here, since we only have one wire connected to the push button, and we have 2 at terminal 3. The other side of the pilot light will be wired to L2 in the starter, closing the circuit just as represented in the ladder diagram. Every time the start push button is pressed, the motor will start and the pilot light will be lit. We can see that it is easier or more convenient to follow the sequence of operation of a control circuit in the ladder diagram rather than in the wiring diagram. However, if you are troubleshooting the circuit and the motor load, it is better seen in the wiring diagram, which described precisely where you would have to look in the starter for the components to test. Both circuit diagrams are useful when troubleshooting. If this motor had been a high voltage motor of, let's say, 480 volts, then we would have used a control transformer for the power to the control circuit, and the connections would have to be made like this in the wiring diagram. The power would now be reduced from 480 volts to 120 volts. This transformer will most likely also be located in the same enclosure where the starter is housed. Note that we have also added overcurrent protection for the control circuit using a fuse. This fuse could have been placed in other locations using other methods, depending on the local, state, or NEC rules. During the designing or troubleshooting of a control system, you will encounter 2 types of circuits which are commonly known as 2-wire and 3-wire controls. These 2 circuit names may be referenced by some equipment manufacturer or by the maker of some motors and motor starters. We actually have covered these circuits without having to describe them with a 2-wire or 3-wire control nomenclature. However, we want to go over it here to avoid any misunderstandings and/or problems, especially when you are troubleshooting a system and find these circuits described somewhere in the wiring or ladder diagrams. So let's take a look at these circuits. 2-wire control circuits are used in applications where the system operation is automatic, which does not require operator intervention. This control circuit is called 2-wire because only 2 wires are connected to a coil in a motor starter, thus making the control circuit appear as one circuit in series driving the logic to a coil. 2-wire control circuits are generally used in circuit applications which are controlling a load device at a remote or distant location. For example, in the control of pumping stations, HVAC systems, compressors, line pumps, and others. Because of the way a 2-wire circuit operates, it is said that this circuit provides low voltage release, but no low voltage protection. This simply means that in the event of a power loss occurrence in the control circuit, the contactor in the starter will be de-energized, or in other words, create the low voltage release from the control circuit and will re-energize if the control device, in this case the float switch, is still closed when the power comes back to the control circuit. There is no low voltage protection because there is no way for an operator to intervene or reset the circuit if a loss of power has occurred. Therefore, you must be cautious when troubleshooting 2-wire circuits, because if you disconnect the control power and the control elements driving the 2-wire circuit are still closed, the coil will be picked up as soon as you put power back on. There is no reset to provide the low voltage protection in the control circuit. This is primarily why this circuit is used in applications that require automatic action for a motor to go back on after a power failure, such as in the case of the control of an air compressor or fan in an HVAC system. As we can see in the wiring diagram of the pump circuit, there are only 2 wires connected or driving the logic of the coil in the starter. Note also that in a 2-wire circuit, terminal 2 of the starter is not used. The 3-wire control circuit, as its name implies, uses 3 wires to connect to the coil of the motor starter. In fact, the extra wire is the one that connects the auxiliary contacts which seal the start push button. In a wiring diagram, the 3-wire circuit looks like this. Here, we can see the 3 wires that go to the starter. 3-wire control does provide both low voltage release and low voltage protection. If the control power is lost, the starter coil will drop, therefore turning off the motor, providing the low voltage release. If the control power comes back up, then the circuit will not turn on the motor unless the operator again presses the start push button. So this circuit is providing the low voltage protection by not allowing the motor to turn back on automatically without operator intervention. The 3-wire circuit can also be visualized in the standard push-button station used for 3-wire control. As you can see, there are 3 terminals for the 3 wires. Terminal 1 goes to L1, and terminals 2 and 3 go to the auxiliary set of contacts in the starter. This typical push-button station, as we know, would look like this in a wiring diagram. There are some other 3-wire control push-button stations that may incorporate additional components, such as a jog selector switch like this, to implement the motor jog function. In this circuit, the selector switch would be used to run the motor in the standard manner. That is, if the start is pushed, then the motor will be turned on. If the switch is in the jog position, then the motor will only be able to turn on when the push button is pressed. As soon as it is released, then the motor will be off, thus allowing the motor to jog every time the start push button is pressed. The jog selector essentially eliminates or breaks the memory effect that the sealing auxiliary contacts provide. This station will be represented in a wiring diagram like this. As you can see, this circuit still represents a 3-wire control circuit. In this next section of the program, we're going to look at the causes that make a motor fail, so that we are constantly aware of them, especially when troubleshooting the motors and their power circuits. Motors are essentially the workhorse of a manufacturing plant. They're designed with the intention of lasting for a long time. Just look at the personal relationship we have in our daily lives with air conditioning units, refrigerators, and others. They all have motors and are meant to last. However, due to wear and tear, they eventually will fail due to aging, and when that happens, we need to replace them. Unfortunately, not all motors end their lives from long service. Because of conditions that are experienced in the plant, many motors have their working life reduced or even ended. These are the matters we must anticipate before these conditions get to our motors. Most often, motor problems give symptoms of abnormal operation, such as running very hot, running noisily, or at a slower speed than normal, and even failing to start. Each of these symptoms will tell us that the motor is not operating properly and that we must pay attention before long. We need to use our sense of smell, touch, hearing, and feeling at all times in order to detect some of these problems. The reason the motor failed is important because even if we had to replace it, we need to ensure that the problem does not stay in our system. The same thing applies if we need to change our car tires because they wore out early. We would need to investigate the reason. If poor alignment was the cause to change our tires, the new ones are going to experience the same problem and we'll be back to square one again if we do not fix the alignment problem. The reason for motor failure should be investigated and documented in the maintenance replacement report. We know that regardless of how well built a motor is, one day it will fail in spite of how well protected it is. The major cause of motor failures is related to the deterioration of insulation. Although most motor manufacturers have attacked this problem, it's still the weakest link in any motor. This deterioration in the insulation is usually caused by excessive temperatures experienced by the motor and its windings. The main causes for heat problems in motors are excessive loads, excessive duty cycle, high or low line voltages, imbalanced voltages, single phasing, high ambient temperature, and the lack of proper ventilation for the motor. If the motor is required to do more work than it is designed for, it will attempt to do it by pulling more current, thus resulting in a temperature increase. We know that if an overload condition occurs, the motor's overload will disconnect it from the line. However, this should be the exception, not the rule, if it is happening continuously. In fact, if we have a motor with an automatic overload reset, the motor can be cycling until enough heat is built up to deteriorate the motor winding. It's a good practice, once we have replaced a burned-out motor, that we measure with a clamp-on meter the current being drawn by the new motor. The closer the reading to the full current rating of the motor, the harder the motor is working with that load. If the current being drawn is very close to the maximum current in the nameplate, then perhaps we need to go to a larger motor. This can serve as insurance for later on in case the normal load increases due to changing in pulleys, gear sizes, or more load resistance caused by wear on the equipment being driven. Excessive turning on and off, or jogging, or reversing can be harmful to a motor because, as we know, it draws more current every time it is started. This creates heat buildup because the continuous self-cooling effect of the motor rotation is lost. If it is necessary to have a heavy-duty cycle, the proper motor should be chosen to start up with, and perhaps choose one of higher horsepower than required by the load. Although motors are very tough, they are sensitive to their rated voltage. They are designed for operation within a 10% voltage for which they are rated. A lower incoming voltage has an effect of lowering the motor's starting torque and an increase in full temperature rise. A higher incoming voltage has the effect of a higher starting torque and current. This higher current causes saturation of the iron and a rise in temperature. If a motor is running at more than 10% above or below its rated voltage, it could shorten its life. So when we replace or install a new motor, make sure you check and document its incoming voltage to that of the nameplate. We already know the problems an imbalanced line can cause, and this is especially true with motors. In fact, this can be the silent killer of motors because it is not easily recognized until some damage has already taken place. An imbalanced voltage is a source of heat by creating a current imbalance in the windings. This, in turn, also creates the first symptoms of a decreasing torque, more noise and vibration. So, to prevent this, which should be done during our preventive maintenance, we need to make sure and document that our phase voltages are very close to each other. This can be easily done by measuring each line voltage. We know that single phasing occurs when one of the phases is lost due to a blown fuse or tripped breaker or an open switch or contact. If a single phasing problem occurs while the motor is running, an increase in slip will occur, or in other words, there will be a decrease in RPMs at full load. The motor will continue to run as long as the torque requirements of the load are not greater than the motor torque. This condition increases heat and vibration, which will cause severe damage to the motor if not disconnected promptly. If the single phasing occurs with the motor at rest, then it will most likely not start with the load, and it will give a hum sound if it is started. If an electrician or technician assumes that the motor is bad and changes it, the same will happen to the new one. We must check the incoming voltages for a missing phase. A single phasing condition at rest could also cause a three-phase motor with a small load to start in either direction, which could cause damage to other equipment. Just like in the case of high current, a high surrounding ambient temperature can cause the same unwanted results to a motor. This can occur because the motor is operating in a tight location, or if it is subjected to high external or ambient heat. One of the major problems here is that overloads do not detect this problem since they are monitoring the current for heat creation, not the ambient. So if a situation like this persists, the motor can burn up without detection. We need to make sure that we know exactly at what ambient temperature the motor will be working so that it doesn't exceed its rating. Insufficient ventilation can occur to a motor when the air passages within the motor are clogged with dirt or other material and prevents or blocks the natural cooling effect of the motor. The motor under these conditions can reach high temperatures without increases in current, which means that it can go undetected until it is too late and burn out. This should be an extremely rare problem if proper preventive maintenance is performed.